Hi, everybody. We're going to talk about the final topic in our Chapter 2, which is our Introduction to Logic. And this is one of those topics that's going to be super important when we start getting into proofs. And that is, how do we simplify when we negate a statement? Now, negating a statement by itself is easy. If you have any kind of statement, I'll just write P, but it could be any logical statement, no matter how complicated, combinations of things, whatever. You can negate it by just putting a negation sign in the front. And that means not P, or it is not the case that P. And I kind of think of negation as it's a little bit like the logic equivalent of multiplying by -1. It's saying do the opposite of whatever was there. All right. So the thing that we're really interested in is, just like in algebra, when you multiply by -1, you can often simplify the result. We can simplify the result here when we negate a statement, but the simplification depends on how that statement was built. So here I had just a simple statement, P, but the question is, what if instead of P, what if we had something like a statement that was built out of other statements using one of our logical operations, like conjunction, disjunction, the conditional, a universal quantifier, or an existential quantifier. So these 5 items are the ones that we need to be able to negate. So let's talk first about the rules. I'll just go through them relatively quickly, but I'll try to do 2 things. I will both state the rules, and then I'll also talk about what is it that the rule kind of means. Can you think about it in terms of logic, in terms of statements and truths and falses, to understand what it means? Okay, so we're going to go ahead and start here with conjunction. So for conjunction, suppose that we have a statement P and Q. And now the negation of that statement is not P and Q. And if you think about what this means, P and Q means P and Q are both true. That's the meaning of the conjunction. If it is not the case that P and Q are both true, that's what the negation means, not P and Q. If it's not the case that P and Q are both true, then at least one of them has to be false. So what we have is either not P is true, that is, either P is false, or not Q. Q is false. So this equation right here gives our first rule. When you negate a conjunction, when we have not both P and Q, then what you get is either P is false or Q is false. Not P or not Q. And this is one of the 2 De Morgan's laws. Okay. Secondly, disjunction. Disjunction, we start with P or Q. And remember, what disjunction means when you think about how to express it verbally is it means either P is true or Q is true or both are true. And now if we negate that, if it's not the case that either P is true or Q is true or both are true, the only option that's left is that they're both false. And that means that P is false and also Q is false. Not P and not Q. And this is the other of De Morgan's laws. And the way I look at these is they're a little bit like a distributive property. You can distribute the negation through the parentheses with a conjunction. And what it does is it applies the negation to each of the 2 pieces, and then it flips that conjunction over into a disjunction. Similarly, you can apply the negation through a disjunction, through an or, and it applies the negation to both pieces, and it flips the or over into an and. Okay, so these are sort of our first 2 rules, and we've seen those before. Let's look at some others. So let's look at the conditional. So the conditional statement is if P, then Q. And if we negate that, if we say it is not the case that if P is Q, then Q must be true. And we ask, what does this mean, really? Well, let's think of it this way. The only way that if P then Q, the only way this statement comes out to be false is if the first thing is true, but the second thing is not. Because this is like a promise. If P is true, then Q has to be true. So if this if-then statement is false, if we negate it so that that if-then statement is no longer true, the only way that that can happen is if in the following combination, the first thing is true and the second one is false. So let's just write that down. The first one is true and the second one is false. So this one I feel like is a little surprising when you run into it without thinking through it in that way. It says the negation of a conditional statement, if P then Q, is P and not Q. It's the combination of the first thing being true and the second one being false. And that one, to remember it, it just helps to think, what's the only way that this if-then statement can fail? What's the only way it can be false? It's if the first thing is true and the second thing is false. Okay. Now let's talk about our quantifiers. So this is the universal quantifier. It says for all x, P of x. So we write P of x here to represent just any logical statement about x. So this might say for all x, P of x might express something like if x is divisible by 3, then x is not prime, something like that. And the P of x, we just use that variable to say any property involving x, any statement about x here. This says that no matter what x you choose, or no matter what you choose to put into that variable x, if you plug it in here, this statement comes out true. That's what for all x, P of x means. Now, if we negate that statement, not for all x, P of x, well, if it's not the case that for every single one of these x's, it plugs in here and this is true, then if that's not the case, then there must be at least one x that makes this false. So we would write it like this. There exists an x such that not P of x. That is to say, the negation of the statement for all x, P of x, is there is an x such that not P of x. This is a little bit like saying if it's not true that P holds for every x, then there is an x for which P does not hold. If you look at this sort of in terms of algebra, it's like this negation passes through the universal quantifier and applies to the thing inside, but it changes the universal quantifier into an existential quantifier. So as you're trying to kind of remember how these look, how the syntax looks, how the symbols look, that's kind of the way my brain thinks of it, is the negation comes through the universal quantifier and converts it into an existential quantifier, and then the negation applies to the thing inside. All right, there's one more of these, which is the existential quantifier. Existential quantifier. This one says there is an x such that P of x. Now, this statement, the existential quantifier, says that yes, you can actually go and find an example of an x and plug it into P of x and it will be true. It will hold. Okay, and what we want to do is negate it. So what happens if it's not the case that there's an x such that P of x? Well, if it's not the case that you can go and find an x such that P of x holds, it must be true that for every x, P of x fails. Yeah, that's the only way that you could not find an x where it works. So I would say this says for every x, not P of x must hold. And this one says the negation of an existential quantifier. The negation passes through the existential quantifier, applies to the thing inside, and that existential becomes a universal quantifier. You'll notice these two rules sort of go together. They match each other in much the same way that the rules for and or match each other. And there's a good reason why they sort of line up in that way. Okay, so those are all of our rules. I find looking at these rules, I find them to look quite confusing, but if I can think through the meaning behind them, then they make a lot more sense. So let's go ahead and actually talk through some examples. Here we go. If you're wondering what's up here, this is just the rules for negating statements, some of the rules that we wrote down. The list I have here is even more complete, so stick with that. All right, this was example 4 on the handout from last time, and we're going to go through it today. That'll be our last foray into the logic chapter, and then next we're going to talk about something called combinatorics, which is the science of counting. Okay, so let's talk about example 4. It says, find the negation of the sentence, both in symbols and in words. So here, R is the statement X and Y are both odd. And we want to know, what does the statement not R say? So if R is the statement that X and Y are both odd, and if that's false, well, if that's false, then either X is not odd or Y is not odd. So it's like this, X is not odd, or Y is not odd. Remember, when we use the word or, it means either this or both. So either one or both of them must not be odd. That's the negation of the statement X and Y are both odd. That's what happens if it's not true that X and Y are both odd. And this is just using De Morgan's law. We have this word and, that's a conjunction. The thing that's being conjoined here, the two parts of the conjunction are X is odd and Y is odd. And what we do is, when we negate that statement, we apply the negation to each one individually. X is not odd, Y is not odd, and we change the and to an or. Okay, let's see. Next, all prime numbers are odd. So the statement is all prime numbers are odd. What I'm going to do in this case is I'm going to first translate S into symbols. Let's do it something like this. For all X, if P of X, that is, if X is prime, then O of X, then X is odd. Where I'm just making up letters to symbolize these properties, P of X for X is prime, and O of X for X is odd. Okay, now let's go ahead and negate this. So not S, it's the negation of this for all X, P of X, then O of X. Okay. So I want to do this in two ways. I want to first think about the meaning of this statement, and then think about what it means for this statement to be false. Okay. And then separately, I want to think about the rules that we have for negations, how we can take this negation and distribute it through, and what happens to the resulting things. And we're going to see, hopefully, that they come out the same. Okay. So let's see. All prime numbers are odd. Okay, what's the negation of that? If it's not true that all prime numbers are odd, then there must be a prime number that's not odd. So if not S holds, this is like, there must be a prime number that is not odd. And how would we write that down? Well, there exists an X such that, what, X is prime, and it's not the case that X is odd. This is meant to be a negation here. So there is an X such that X is prime, and not X is odd. Yeah. So this is just by thinking through what the meaning of the statement was and what would happen if that was false. That's like thinking about the negation. And this is what we came up with. Now, let's go ahead and follow our rules for negations and apply them to this. So this is going to be like a little work we're going to do to the side here. So I'll do it in a different color so we can keep it straight. Oops. All right. So what I want to do here is first move that negation sign past the universal quantifier. I'm going to apply the negation sign to the parentheses. So for now, I'll just keep the negation sign right here. And when we do the negation through a quantifier, we switch it to the other kind of quantifier. So that becomes an existential quantifier. I'm going to do this in sort of two parts. So this is like step 1. It becomes there exists x such that not p of x, if p of x, then O of x. And then let's do step 2. What I'd like to do now is apply this negation to the thing in parentheses. The thing in parentheses is a conditional statement. And the negation of a conditional statement, you'll remember from our rules, is the negation of a conditional statement is this occurs exactly when the first one is true and the second one is negated, is false. So P and not Q, that's what we remember. So you'll notice that for this conditional becomes a conjunction. The thing in the front stays the same, and the thing afterwards has the negation added to it. So I'm going to do just the same thing here. I'm going to apply this negation to this conditional, and that's going to keep the thing in the front the same, change this to a conjunction, and make this a negation of that O of x. So this is step 2. I'm going to keep the exists x that was out in the front, and then we have the P of x and not O of x. And you'll see that the answer that we got here, it matches the answer that we got by sort of thinking things through. So there's like a matchup between these rules, which is like following the symbols, and also just the idea of it, which is following the meaning and thinking about how to negate it. Okay. This is the same answer as this, and they both mean the same thing as this one in words. So this is, they said, express the answer in words. Here it is in words, and also in symbols. There it is in symbols. Okay. Let's take a look at the next one here. We'll change back to my purple. This was A, this was B. Let's take a look at C. For C, we have the square of every real number is non-negative. So just a note on what it means. See, the original statement, the square of every real number is non-negative. So if you have every real number, that's like the for all. If every real number, if you square it, then you get something that's, what does non-negative mean? Non-negative just means, well, it means it's not negative, and that means either it's positive or it could be 0. And another way of saying that is that it's bigger than or equal to 0. So just to state, the original statement says, let's see, for all x in the real numbers, x squared is bigger than or equal to 0. Now, very often when we want to talk about something like real numbers, we just include that with the quantifier, and we do that here as well. An alternative would be to say, for all x, if x is a real number, then x squared is bigger than or equal to 0. That would be an alternative approach, would mean the same thing, and would be just as good. So we're going to stick with this, as it's more like what you'll see in the future. So that's the original statement. For every real number, x squared is greater than or equal to 0. And now we're going to negate that statement. So what is, it's not the case that for all x in R, x squared bigger than or equal to 0. What would that mean? Well, just thinking through what it means logically, if the original statement says, for every x, this thing is true, then the negation of that statement says there must be at least one x where this fails. Yeah. So we could write it, there must be an x in R such that x squared is not greater than or equal to 0. Of course, you could replace that not greater than or equal with is less than 0. That would be just fine. But that's just because we happen to know that the negation of this is things less than 0. We know that numbers split into negative, 0, and positive altogether. So if something is not greater than or equal to 0, it's less than 0. Just like in the previous problems, I chose to leave it as not odd instead of saying even. because the fact that that numbers are not odd, that non-odd numbers are even numbers, is something that we will prove. That's not a fact that we're going to take for granted. Okay. And if we want to write this, so this is our answer, and if we want to write it in words, we would say something like, there is a real number whose square is not... Oh, let me see. Well, expressing things in words, I could say is not greater than or equal to 0. But this said every real number is non-negative. So we could say whose square is negative, I guess. Is negative. Or is not greater than or equal to 0. That would work too. Okay. Okay. So... here's our final answer in symbols. Here it is in words. All right, let's take a look at D. For every real number x, there is a real number y, for which y cubed equal x. Okay, let's write this one down in symbols. First, we saw this perhaps in our last day of class last week, but it's not bad to approach it again. It starts with for all x, for every real number x, so for all x in the real numbers. There exists a y in the real numbers such that y cubed is equal to x. Okay. And what we would like to do is negate the statement, the negation of, for all x in the real numbers, there exists a y in the real numbers, such that y cubed is equal to x. All right, and we're trying to untangle the meaning of this negation. So what does it mean? Well, I want to do it once again. I'll do it in two different ways. First, I will do it... this time, first I will do it by using the rules, and then I will do it by thinking through what it says. Okay. So by using the rules, what I'd like to do is apply the rule that says, if you look at this statement, the outermost thing here is this universal quantifier. So I'm first going to move that negation, pass it through, and it's going to become a negation here in front of the existential, and that for all is going to turn into an exists. So just move number 1. This is like step 1. Exists x in R such that not, there is no y in R with y cubed equal x. If you want, you can stick parentheses around all that, because that negation applies to that whole statement. Now, we're not done yet. What I want to do next is move this negation one more step inside. I'm going to pass it through that existential quantifier. I'm going to apply the negation to the thing that is inside, which is this equation. And I'm going to switch this to a universal. Excuse me. I copied down the stuff in the front just to keep it there. Now, the negation of the existential quantifier gives me a universal quantifier for all y in R, not y cubed equal x. So what does this say? It says there is an x, which is a real number, such that no matter what y you choose for all y in the real numbers, it is not the case that y cubed equals x. This is like saying there must be an x such that no matter what y you give me, you don't get y cubed equal x. All right. We could do one more, which is just what is the negation of the statement y cubed equal x. It's fine to write it like this. You can also write this instead as y cubed not equal to x. So get rid of the negation in front and put a slash through the equals sign, because that's what the negation of an equation is. So this final answer, there is x in R such that for all y in R, y cubed is not equal to x. Now, let's just think about what the original statement was. So first of all, this is our final answer in terms of symbols. Let's think about what the original statement was and then try to untangle what it means, what it would mean to negate it. So the original statement claims for every x that you give me, that's every real number x, I can find a real number y such that y cubed is equal to x. And the way to think about this is like, if you give me an x, then I have to come up with a y, and y cubed is equal to x. And this is saying that I can always do that. I always win, basically. I always can find a y that works. If this is not the case, then there must be some x you can give me such that no y works. Yeah? So if this is wrong, if it's negated, then there must be a real number, x, such that for all real numbers y, we don't have y cubed equal x, or y cubed is not equal to x. And if you think about how this would translate into symbols, it would look just like this. There is a real number x such that for every real number y, y cubed is not equal to x. So here we have the answer to this one in symbols and in words. That's part D. Okay. Let's go ahead and take a look at E. That's our last one. It says, if x is odd, then x squared is even. So let's see, if x is odd, I'm going to write that as like O of x, then, oops, x squared is even. Let's use E to represent is even. So not the existential quantifier, that's a backwards E, but this is just a regular E. This is like even. I believe this says, it's a conditional statement, so it has an if-then built into it. If x is odd, then x squared is even. Now, there's something a little funny here, which is that we have a variable x, but we haven't said what that variable is. In math, it's generally the case that if we make a statement like this without telling you what the variable is, that what we really mean in the front is for all. For all x, if x is odd, then x squared is even. That's what that statement is trying to say. We're not going to worry about that for all out there. We're going to just leave it. We're going to write it down, copy it down exactly sort of as it says on the page. But it's sort of good to keep that in your head, that that's the meaning of a mathematical statement, a logic statement in math that has what we call a free variable, or an open sentence. Is we think if a mathematician says an open sentence that they mean for all x it's true. Okay, so let's go ahead and think about what we get if we negate this. If OX, then EX squared. Well, here we're going to be using the rule for the conditional, and the rule for the conditional says we keep this one, we make it a conjunction, and then we have not this one. So this is x is odd, and x squared is not even. You might go a step farther and say x squared is odd, because not even means odd, but we don't know for sure that not even things are odd things. We're going to get to that later. So I'm just going to keep it as not even for now. So this is OX and not EX squared. That is to say, x is odd and x squared is not even. And here we have our symbolic and natural language versions of this negation. Okay. That's it for negations. You're going to find that this kind of idea comes back and is very helpful to us when we're trying to prove things, or when we're trying to disprove things. Disproving them means proving them false, and that's where that negation in the front will come in. All right, that's it for logic, you guys.